Question today is Punshon-Smith gonna talk about lower bounds on Lyapunov exponents for stochastic PDEs.
Okay, thank you. Yeah, it's nice to be back here. I spent a whole year in IS as a member sort of during COVID. It was a great time, and yeah, it's very good to be back. So today I'm going to talk about a problem that honestly I've been working on for quite a few years. You know, I can give you a little bit of the initial motivation, and then in fact the way we went about proving it sort of very different than the original motivation, perhaps. So the main focus of this talk is going to be studying equations, let's say, that roughly look of this form. For simplicity, you know, we're just going to consider things in the two-dimensional periodic box. And this operator L here, you know, you can think of is generally it's going to be some possibly some pseudo-differential operator that depends linearly on some u. And this u, you know, we're going to think of as some process. Typically in these examples, it's going to be stochastic. And in particular, most of the examples I'm going to give you, the u is going to solve a PDE for a velocity field. Okay. So specifically, I think from now on, let's think of ut. Let's solve the stochastic Navier-Stokes equations. In two dimensions, so in particular, it's going to take the form. I'm going to just introduce a different viscosity parameter here. I will connect this one to this one in just a second. Okay, and then there's going to be some forcing on the equation here. And this force is going to be stochastic. Okay, so specifically, we're going to assume that it's white in time, but sort of correlated in space. Okay, and particularly, we're going to assume that it's non-degenerate. And this is something we'll come back to. It's a crucial assumption. Okay, so to be more specific here, I'm going to assume that the C being essentially a Gaussian random field is going to have the following correlation structure. The average component of C times P, if I Fourier transform, look at mode decay, and look at its correlation, the Jth component, minus A prime. This is going to be bounded above and below by delta ij, so different dimensions are uncorrelated. It's white in time, and then in space, it has a decay that looks roughly like k minus k prime to some negative power a, where a is any number that we just need to be bigger than, for technical reasons, 10. Okay, so in particular, oh, sorry, this is Fourier transform. So in particular, this random field is going to be, you know, distribution valued in time. So it's really a stochastic differential equation, but it's going to be essentially Sobolev regular in space, okay, with some Sobolev parameter that you can pick as big as you like. All right, so this allows me to pick A to be 1 million, for instance. So you don't have to think of anything as being particularly rough.
Minus A.
Minus. Or it's a decay.
You want decay.
And so, you know, for this type of equation, it's essentially a very, very well studied equation, particularly in two dimensions. You know, globally well posed. Okay, in particular, there exists a unique stationary measure. Okay, so there's a probability measure on some Sobolev space, HB, where B is some number between 0 and A/2. That's a stationary measure. So stationary particularly means here that if I were to take the expected value conditioned on the initial value of phi, some test function ut, and I integrate over all the initial conditions, that this is the same as just integrating phi with respect to the same measure. Okay, this is true for all phi. So in particular, this kind of thing gives us an ergodic structure for the dynamics. All right, so because I've given you this very specific structure, but generally speaking, we want to consider this kind of a picture where U is some Markovian ergodic stationary process. So now the examples that we're going to be considering, so just the figs in this case, are going to be one, just the advection-diffusion equation. Where L U is just the advection operator. And the other sort of example of interest is going to be the linearized Euler or Navier-Stokes, if you like, equation. Where L of U is going to take the linearization of at least the Euler nonlinearity in vorticity form. Let me put a function here. I'm going to write it in sort of a special way to 2 dimensions, which is something like this. And this is vorticity form. Okay, so both of these examples are natural linear PD. In this case, both of these are naturally coming from fluid mechanics. So this would be a problem where I'd say, let me study the evolution of some scalar being advected by the Navier-Stokes equations and understand its long-time behavior. Second one comes from just studying stability properties of Navier-Stokes itself. So if you were to linearize the Navier-Stokes equations about the solution itself, we're asking what's the long-time behavior of it. The only subtle point I want to make about this example is that at some point we will be getting estimates that are quantitative in this parameter kappa. And notice I've taken kappa and nu to be different. So this linearization is only going to be the linearization of Navier-Stokes if kappa and nu are actually equal. And we cannot get anything quantitative in nu. We can only get quantitative in kappa. Getting quantitative things in nu is an extremely, extremely tricky problem for turbulence. Okay, so this is the main setup. Now, let me just state sort of what the main goal is. So we're going to study the top Lyapunov exponent. For this process rho t. Okay, so specifically, this is defined to be lambda1 kappa. It's going to be the limit as t goes to infinity, sup over all initial conditions, rho 1 log rho t. Now, this norm I'm picking is the L2 norm. I want to emphasize that this number, in fact, this number lambda that we get for this does not actually depend on the norm that you pick. It's very convenient for calculations for us to pick this norm, but Lyapunov exponents are known to be sort of metric independent quantities. And in fact, I have a paper with Alex Blumenthal in, I think, point 2, where we show that, lambda is norm independent. under some conditions, but it's pick L2, pick H1, whatever it is.
I cannot read from here.
I'm sorry.
The supremum, no, it's on my fault, but the supremum is over what?
Over all initial conditions with norm 1. So this quantity sort of tells you asymptotically what is the exponential growth or decay rate of the equation.
And the initial condition is U0?
Doesn't matter. Yeah. The initial condition this thing does not actually depend on the initial conditions at all. So I fix an arbitrary U0. I take this limit and I only soup over the initial row. Essentially, there's a nice theorem in ergodic theory, the multiplicative ergodic theorem, which says that this limit does not depend on the initial conditions, and it doesn't depend on the noise. So it's a universal number. Okay, so in fact, I'll just say sort of by the multiplicative ergodic theorem, which I'll just call MET, lambda 1 kappa exists. Okay, but when I say exists, this is a very important caveat. It exists as a number that is possibly equal to minus infinity. So it could be. Sorry, I keep seeing my.
Sorry, but what is the equation for PT here? The first you wrote, the general one?
Yeah, this.
And this result is independent on L or
It depends. Yeah. Actually, in this case, it's independent of L. I mean, this one you can show this thing exists, and I think under super general conditions on L, as long as you have some ergodic Markov process, this thing exists. You need some log integrability assumptions on this thing in order for this to exist, but that's pretty much it. So just the existence of this, very, very general. So in this paper, we also frame everything in very general contexts like this. For the remainder of the talk, though, I'm mostly going to be considering these examples. So the two that I have on the board, the advection-diffusion and the linearized Navier-Stokes. And for most of the calculations, I'm just going to stick to advection-diffusion because linearized Navier-Stokes, things get a little hairy.
One question. So I understand that it exists for both choices and for many other choices, but I didn't get it if you're also claiming that its value does not depend on the choice of L.
No, its value does depend on the choice of L. Yeah, absolutely. And the value also depends on the noise in some loose way. But it doesn't depend on the initial conditions of U. And it does depend on the initial conditions on row, although technically it shouldn't. But I
mean, L could be 0, so obviously.
It obviously depends on L. Yeah.
Because otherwise, it sounds too good to.
No. The thing clearly depends on L. I mean, for instance.
But it doesn't depend on U0 because somehow the stochastic thing will make you forget whatever is the initial data, I think.
Exactly. It's the U will settle into some
into whatever it happens, and whatever you started with is essentially irrelevant.
Yeah, it always settles into something that's in the stationary measure, so you don't really see the initial conditions anymore. Exactly. Okay, so all right, so there's a fundamental question we want to ask here. How does lambda 1 kappa depend on kappa?
He says you could also ask the question, how does it depend on mu, but that's harder.
Yeah, much harder, in a way that I have no idea how to even start answering the question. Yeah, unfortunately, that's a very tricky problem in turbulence. Okay, so I'm going to start by actually just stating the main result. And so this is in a paper with Martin Heyer, Tommaso Rosati, and Yi. That was just put out last year. And the statement goes as follows. So, let L of U, be advection-diffusion or linearized Euler, as we have over here. And then assume that U is solving the stochastic Navier-Stokes equations with that non-degeneracy parameter A bigger than 10. Then for any Q bigger than 3, there exists some constant depending on Q, such that lambda 1 kappa, so the top Lyapunov exponent, is bounded below by negative C Q A to the minus. Okay, so we have a quantitative lower bound on the top Lyapunov exponent in terms of inverse powers of kappa. Now, I want to put some of this in context because it's not actually that sort of obvious why you would expect something like this. And in fact, maybe I'll mention that even showing that the top Lyapunov exponent is not minus infinity is already very challenging. Okay, so this is what we prove. So let me give you basically some insights into significance.
So just to understand a bit of stuff. When you say minus infinity, what you should understand is that you are implicitly proving that there is at least one solution that is not decaying to 0.
But
no, it can go to 0 because everything's minus infinity would mean that you decay super exponentially.
Right, you're absolutely right. Yes.
Exactly. So in fact, this rules out super exponential decay. So it shows that you have a linear equation like the advection-diffusion equation, that there are, in fact, there's more strong answers you can get from the multiplicative ergodic theorem that say basically away from a set of positive codimension, everything decays exponentially fast at most. So nothing can go super exponentially. So the significance of this is kind of twofold, right? So one is it actually shows that lambda 1 kappa is not equal to minus infinity. Okay, so this is essentially saying that there exists an exponential lower bound. So specifically, just by some properties of the multiplicative ergodic theorem that I don't want to get into just because it's a little bit technical, you can show the existence of a sort of a random constant, the epsilon, that does depend on the initial U, where the lower bound for any epsilon looks like this lambda 1 kappa minus epsilon to the t times, okay, actually this is fine, like this, for row 0, I'll put in quotes, away from some set E omega U0, which is random, belonging to this belonging to L. Okay, where the codimension of this set is. Okay, so you have a finite exponential lower bound. You say that pretty much generically, most initial conditions have to decay no faster than exponentially fast. Now, I want to state that this, if I give you an arbitrary velocity field, it's still a wide open problem to prove that the equation cannot decay faster than super exponential.
Is the sign correct?
Oh, I'm sorry, you're right. Lambda is negative, so that's right, yeah. Thank you. So the problem let U just be some bounded Lipschitz velocity field can rho t based super exponentially. Okay, and I want to emphasize this is on bounded domain. So if you're on unbounded domains, much easier to do this kind of stuff, but on bounded domains, it's a little bit trickier. Okay, so this is unknown. All right, but essentially what we show is that in the case of random velocity fields, you can't have it. So basically, the only way that you could decay faster and exponentially is if things kind of conspired in a very special way to do it, and random velocity fields don't do that. Okay. So now there's one more consider, and this is known as the Batchelor scale. So George Batchelor in 59 basically conjectured that if you look at mixed scales for advection-diffusion equations, so let L mix, you can think of something, for instance, there's a lot of ways to define mixed scales, but let's consider something like the H-1 norm divided by the L2 norm of the scalar. This has the units of a length scale, and it, roughly speaking, is the scale at which the scalar will be mixed. You could use something like a Bersan type norm as well, or an H1/2 or whatever, as long as it has units of length. But this thing is when t goes to infinity, the advection and the diffusion kind of balance each other out, and it settles to something that's roughly the square root of kappa. Okay, so mixing eventually gets halted when you have diffusion. It's not terribly surprising, but in fact, it's incredibly hard to prove. So this conjecture has more or less remained open, even in any almost no known examples where you can actually prove that this is true, despite kind of overwhelming numerical evidence. And you can link this to the Lyapunov exponent very cleanly. Okay, so kind of naturally, what you can say is, let lambda 1 that's kappa. This is, of course, if I just use energy methods, if I take the log of the L2 norm of the advection diffusion equation, this is actually just, 1 over t limit. One over t is sort of the average of the energy dissipation. And this is integrated time. And I can compare this to the length scale. Oh, sorry, these should be squares. And I can compare this to the length scales just by interpolation or whatever. And so this whole thing is going to be bounded from below by the limit as t goes to infinity 1 over t, the integral from 0 to t of kappa times this mixed scale minus 2. Okay, and if the mixed scale is roughly order square root of kappa, then this thing should be roughly order 1. Okay, so what this is saying is that you have sorry, did I get the direction right? Yes, that's right. So this is saying that you should have a bound on the top Lyapunov exponent, which you expect to be roughly uniform in kappa. Okay, so this actually yields the following conjecture that you should expect, in fact, in many cases, that lambda kappa, at least when kappa is small, to be sort of uniform. Oh, sorry, minus 1. Did I miss the signups?
No. I was just.
Okay, so one of the directions in this, in fact, has already been proven. This was proven in early work with Jacob Bedrosh and Alex Blumenthal and myself, who let's say one of the bounds is essentially just equivalent to uniform diffusivity mixing. The lower bound is essentially equivalent to the existence of this Batchelor scale. Okay, so we're going to focus basically on just one of the bounds. Okay,
So this bound is really for large kappa, is it?
Small kappa. Oh, did I say infinity? Where did I,
Kappa is going to zero.
kappa is going to zero.
Kappa is going to zero.
Yeah,
Cap is going to zero.
kappa is going to zero. Yeah, we want to think everything
That's what I
asymptotic and
thought,
small
yeah.
diffusive.
But you have, oh, that's the conjecture.
That's the conjecture.
Yeah.
We're not going to be able to prove the conjecture fully, so we have sort of a partial resolution of it, but in fact, it's still pretty tricky to get, even in this setting. Okay. So let me talk to you about some of the ideas of the proof. So essentially, I'm going to introduce something known as the projective process and something called the Furstenberg-Kosminski formula. Okay. So the idea here is that we kind of turn this problem into studying the L2 normalized process. So take rho and divide it by its L2 norm. And this belongs to the unit sphere, L2. And in fact, this calculation that I did over here can be written in terms of a time average of that projective process. So in fact, one of the things you kind of see is that, lambda1 kappa can in fact be bounded below by -1 over t, the integral from 0 to t of just the gradient of pi s, or kappa times the gradient of pi s squared ds. Okay, so this is some long time average of this process. It's, the process US IS is in fact a Markov process. And so if this thing has a stationary measure, then you expect that this thing should be able to converge to at least a stationary measure as t goes to infinity, just by ergodicity. Okay, so this thing should converge to some average, over the appropriate phase space. So in this case, just over the unit sphere of kappa times d nu. No, I should say I'm really integrating over the phase space for u and s. Okay, this is assuming nu as a stationary measure exists. Okay, and so this kind of argument that I made over here, we can actually say that there's a formula more or less that pops out. Sorry, it should be a minus sign. It says lambda1 can be bounded below by some average with respect to some stationary measure of the H1 norm of this process. Okay. However, this leads to two problems. First one is, does such a stationary measure actually exist? And that turns out to be a very hard problem. And question two, can you get moments? Of the H1 norm with respect to this measure? Right, so this can really be turned into a question of, I have an infinite dimensional Markov process that's evolving on an infinite dimensional manifold, and I'm asking, does there exist a stationary measure for this process? Now, maybe for those of you a little bit more acquainted with theory of Markov chains, proving the existence of a stationary measure usually comes down to proving the existence of a Lyapunov function that satisfies a well-defined drift condition. So can we find a Lyapunov function? Okay, and a Lyapunov function is going to be some object that has compact sublevel sets, where on average, you're sort of returning to these sublevel sets infinitely often, with very tight control on how quickly you return. The problem here is that this phase space is not compact. And so it's very hard to find a good compact sublevel set of this thing that you're going to return to infinitely often.
So in a finite dimensional case, you wouldn't have something.
Finite dimensional, you're done. It's a compact space. There exists a measure by snap of the wand or fingers, right? Infinite dimensions, it's very tricky. And let me just sort of give you an intuition of what you're fighting. I mean, you have this feature that possibly pi could be sending all of its mass to high frequencies in some way or another, right? And so if you just keep going to higher and higher frequencies, you sort of lose this H1 norm would blow up, and possibly you sort of lose probabilistic information. Okay, so pi t could be going to high frequencies. However, we do prove the following result. So in fact, we prove essentially an equivalent statement. So namely that there exists some time that's at least big enough such that the expected value of pi t0 L2 squared is less than up to some constant k to the minus, I think the q is going to be plus 1 or 2q plus 1. Sorry, such that for every q bigger than 4. Okay, we have an estimate like this, and then there's some function here that depends on the velocity field that I'm not going to make explicit. Okay, so this is saying that, okay, let's think of this in possibly two ways. This is an estimate on the regularity of pi t0, and notice the right-hand side doesn't depend on pi 0 at all. Okay, so this is really like a regularization estimate, okay, because we know pi 0 is L2 mass 1. You could, of course, think of this in terms of P0 L2, which is just 1. And so this is a Lyapunov function estimate. In fact, it's an extremely strong Lyapunov function estimate. It's just saying that the average of this thing is just bounded by something that's completely uniform in the initial conditions. This type of an estimate it essentially immediately implies that there exists stationary measure nu. Okay. And then if I integrate both sides of this equation with respect to that stationary measure, I get the finite moments. Okay. And in fact, this estimate is exactly the estimate that we got on the Lyapunov exponent if I just plug that bound I got into here. Okay. So proving this is good enough. You can prove that there's some time long enough that this is true. It's sufficient. Okay. We're just building a Lyapunov function for the process. Now to do this, we have to actually do some math somewhere. So
for this, like this kind of inequality, which is to be like L2H1 regularity, there is nothing similar in the deterministic setting, right? Or this comes from a deterministic equivalent.
This kind of estimate, is very hard to prove for the deterministic equation. I mean, to sort of mention, I think if you think about it, dt I, because I've L2 normalized it, if we just do the advection-diffusion equation, it solves a nonlinear equation, right? So it's actually going to be equal to pi and then this sort of cubically nonlinear source term like this. So you're trying to get, oh, sorry, there's a diffusion. You're trying to get parabolic estimates on this. This term really messes it up. So I don't know of any easy way to get regularity estimates on this equation. If you did, you would have solved the problem already. So this is a tricky thing to estimate. But the idea is that we introduce a concept that we call high frequency stochastic instability. And the idea is basically that high frequency states are unstable with respect to the noise. So if this thing does go to high frequencies and it's very concentrated at a high frequency state, you add a little bit of noise and that destroys it on a very quick time scale. And we have to make that somewhat quantitative, but that's how it goes. So let me just kind of give you a loose picture. So high frequency states. Unstable with respect to the noise. So here, the example I want you to think is let's just think very, very simply about the heat equation normalized to be on the unit sphere. This is a very easy example to see, but in this case, you're looking at the following process, which is dt pi minus kappa plus pi is equal to kappa pi, this h1. Okay. And one of the things you can easily see from this equation is that pi k, if it's a normalized eigenfunction of the Laplacian, is a steady state. Okay. And that's just because you're normalized to be on the unit sphere. It's kind of obvious, right? But that means that every single one of these things are steady states for the equation. And there's kind of a nice picture you might be able to draw for this. So imagine this is our unit sphere in L2. Let's imagine this to be one of the lowest frequency eigenfunctions for the Laplacian, and then let's say one of the higher ones, and then an even higher one. What you see if you take a look at all these things which are steady states, if you linearize about them to see how stable they are, you see the lowest frequency ones are the most stable. Okay, so that everything is moving into it, but then high frequency ones are unstable with respect to low frequency. So E1 would be unstable in this direction, but stable in this direction. And then E2 would be unstable with respect to all the other ones, sorry. Okay, but it would be stable with respect to the even higher frequencies. So on. Okay, so even though all of these things are steady states, if you imagine something could knock me off of this just a little bit, I would sort of work my way through these things and slowly drift down towards zero, towards this guy. Okay, so some adding a little bit of noise to this thing perturbs this picture. Now, I'm not giving you the best picture of this because when you add a little bit of advection wants to create high frequencies. So there's some push, there's something that's pushing me up to high frequencies as well. At some point they have to balance. All right, but this mechanism here is showing you that even for the heat equation, despite all these steady states, if you were to knock off these things, there should be some slow drift towards the lowest frequency states. So basically, to prove this, we introduce sort of a gadget that we call the spectral median. So I'm going to denote for any function on the unit sphere in L2, m pi to be, the smallest number m, such that the high frequencies are controlled by the low frequencies. Okay, so these are modes greater than m, and these are modes of less than number m. Okay, so I think it really helps to draw a picture for this as well. If we were to plot the Fourier transform of pi, the square of this thing, let's say, with respect to frequency, we would end up with some kind of distribution like this. And because this thing's on the unit sphere, it has mass 1. So this is really like a probability distribution, if you like. And this thing is really the median in terms of as a probability distribution. So it's the midpoint, or whatever you like. All right, and in fact, if you think of it, the H1 norm that we just looked at, the square of the H1 norm is just the mean of this distribution. Okay, we're just summing up the K's times this thing squared. Okay, and we'd like to understand how this thing evolves under the evolution of the projective dynamics. Okay, so if M slides off to infinity, we don't have a standard measure, and then we would lose the Batchelor scale. If M settles into a particular number, particularly something that's like inverse or kappa to the -1/2, then you have the Batchelor scale. So the goal is to understand what is the long time dynamics of this M. Okay. And so, all right, we have the following results. So let the drift downwards. Okay, so what I'm going to do is I'm going to introduce a time scale. I'll call it T star kappa of M, which is going to be some number lambda times kappa over M squared log M. And this is basically a diffusive time scale. At frequency M. Okay, so this is, if you had a Fourier mode that was exactly concentrated at frequency N, evolving under the heat equation, if you wait times like this, you actually finally see decay in Fourier. All right, so this is how long you need to wait to see it, right? And this is the log is here just saying I need to wait a little bit longer than 1 over M squared. Oh, sorry, kappa inverse. Okay, then what we show, in fact, is that oh, there it is, a lemma. If the median of the initial thing is large enough, then the probability that the inf all t between 0 and then this time scale T star kappa of M waited just a little bit longer, so I'm going to multiply it by some delta of M of pi. The probability that this is less than its initial data -1 goes to 1 rapidly, sort of as fast as any polynomial in M as M goes to infinity. So let me sort of say that in real terms. The probability that M decreases by 1 from where it started on very short timescales. So this would be, I'm looking at timescales that are diffusive timescale, just a little bit longer, and delta here, we're going to think of some number that's going to be very small. It approaches probability 1 as I take M to infinity. The higher and higher frequency I go, the more likely I'm going to see that the median will drop down by 1 very quickly. All right. And arguably, this is the key estimate. Once we prove this, the rest of it, it's not exactly straightforward, but it's more or less a simple exercise in Markov chains. Okay. So let me just give you a rough idea on how this type of an estimate is proved. So once we know that if you start at a really, really high frequency, you immediately have to drop down. We prove this by basically a sort of a lower bound. On low frequencies. And so the idea is actually as follows. So what we show, make sure I get the statement correct. Right. If m it, sorry, state it differently. If m of pi 0 is big enough, then probability that the projection onto just the first set of frequencies for the Laplacian of rho at timescales t star kappa of m to the delta L2, probability that this is bigger than m to the minus a plus 4 times rho 0 L2. Sorry, I need a kappa minus 1/2 here. This probability also approaches 1 as m goes to infinity. I'm being a little, the bound is much more quantitative. It's sort of 1 minus some inverse power of m. As m gets really big, it gets arbitrarily close to 1. So what this statement is saying is that if I look at my equation and I look at timescales that are again just a little bit longer than the diffusive timescale, then the probability that I have populated my low modes by some amount that is an inverse power of m becomes very high probability. Okay, and let me show you about sort of why that implies that the median has to go down. Like first, it's good to just draw a picture for him. Imagine I look at my distribution. Okay, so here's my distribution in Fourier again. I draw it a bit differently. And suppose here's m, and let's say we're in some really bad situation, possibly, where all of the mass is mostly concentrated around frequency m. If that were true, the advection just wants to slide it off to infinity. All right, but what we just showed is that on very short time scales, with high probability, we have to increase the low mode somewhat. And essentially what this means is that the peak ends up getting fatter. So if it were very concentrated, if m is very large, we get this sort of thickening effect. Because the peak just thickened, we now have we can now rely on the diffusion. Okay, because this thing always has to have mass 1, the diffusion kills this side faster than this side, and so there's a shift that happens downwards. And so if I have diffusion, right, then we end up seeing this picture slide downwards.
Were you using the randomness in the first arrow or not?
This is randomness, yeah. So this is noise. All right, and in particular, non-degenerate noise. All right, because what's happening here is that we're relying on high frequency interactions to cancel high frequency interactions and produce low frequency ones. Okay, so the noise fattens it out and then the diffusion balances again. All right, and again, the higher m goes, the stronger this effect is. And in particular, also the stronger effect this is. So let me give you a few more ideas on how this is proved. All right, so let's suppose that m of pi t is bigger than some m for all t from 0 to the diffusion time. Okay. If that's true, then it tells me that all of my mass is mostly at high frequencies. So this in particular means that rho t and L2 is comparable, bounded above and below, by high frequencies. Projection rho t. Okay, it's just what it means to have the median bigger than m. And these are the kind of tricks we play. So we say, let's suppose this is true, then we know that everything is controlled at high frequencies. If I'm only looking at high frequencies, then I can bound by something that's like e to the minus kappa m squared. Sorry, the sup and t. Let's write this as e star kappa. And then times some function that I'm not going to be super precise. It depends on the velocity field. Okay. Now this thing, if I look at it on that diffusive time scale, which unfortunately I erased, but it was 1 over kappa m squared log m times lambda. This thing is exactly m to the minus lambda. Okay. So what it tells me is that if my median is bigger than m for m large enough, then the high frequencies have to be bounded above by m to the minus lambda times some random constants that can be controlled. But I also have a lower bound that says on that same time scale, I have an increasingly high chance that it's also bounded below by m to some other negative power. Okay. And so if I pick m big enough, you get a contradiction. Okay, this can't be less than this and have the median bigger than m and the lower bound. So it's saying that because high frequencies are crushed so quickly at large m, that's not congruent to having this lower bound. Okay, so that tells you that it can't just be above m. Same kind of argument shows you, in fact, it has to drift downwards by an arbitrary constant. Okay. And I think, yeah, I'll give you one last piece to tell you how, because everything kind of comes down ultimately then to this. Once you know that on very short times, the probability that you go to low modes goes to 1. And this is the meat of the paper. Pretty much everything comes down to this, and the majority of the work is done proving this. So the way that this works, very schematically, is we essentially do a short time expansion. Okay, so we think think of this as a Wiener chaos expansion. Okay, this basically means an expansion of Gaussian things. And it's basically Picard iteration. So the idea is that I can write my velocity field as x plus some function psi uu, and this is just mild form for the Navier-Stokes equations. So if I just reformulate mild form, this is just some convolution with the heat kernel of the nonlinearity. This is this thing solves just the Stokes equations. Okay, so this is Gaussian. We do the same thing for rho. Rho is just the solution to the heat equation plus some other function that is some bilinear thing of u. Right. And then if we iterate this and iterate this, we can expand in things that are all Gaussian, right? Or at least deterministic plus Gaussian. So we have y plus p of x, y plus p of something like psi uu y plus so on. Sorry, psi xx. Okay. And what we see is that we get terms that are deterministic, things that are linear in Gaussian things that are quadratic in Gaussian things, and so on. Okay, and the thing just keeps going. And what we do is we first focus on this. We say, okay, because this expansion is pretty good in short time and our estimates are all in short time, let's estimate this thing on average from below. Now it's Gaussian. Gaussian things are pretty easy to estimate from below. I can take expectations, I can use Ito's formula and so on. We essentially focus all of our energy on just proving this. So notice that this is the same thing as basically taking my advection-diffusion equation and replacing the nonlinearity or the u dot grad rho with x and y. So it's the heat equation perturbed by these two terms. We show that that can be bounded below and with the same lower bound. Okay, and then we spend an enormous amount of work studying all the higher order terms and showing that they are smaller than this one. And if you can show they're smaller than this one, then this is the dominant lower bound. Okay, so that's the key approach you have to use. So this stuff here is very nasty. pages and pages of calculations. It's not very easy to do. But yeah. Okay, I think my time's up, so I'll end there. Yeah.
Thank you very much. Is there any question? Let me start with one. I'm not sure does it have any relevance, the exponent q? Like you say that everything goes for q larger than 3.
Yeah.
You have never, like you mentioned a conjecture that would suggest that in fact that this is not sharp.
Yeah.
But you haven't said anything. Is this 3 sharp in some sense?
No, I don't think it's sharp. It's sharp as far as some of the estimates go. Unfortunately, I don't quite know how to make it sharper.
Another question is it actually relevant? Like someone cares about getting the right behavior with respect to k, or this is not important?
Well, I think if you wanted to answer the question of whether this Lyapunov exponent was bounded before me uniformly, right, then it would say that q was 0, right? And so if you really want to get a precise estimate on the Batchelor scale, that's probably it. You know, I don't even know if it's true. It's hard to say. I mean, it probably, the conjecture is probably correct. But maybe there are deviations. I don't know. It's not immediately clear to me. And I think, if you had velocity fields that were rougher than in this case, which were all in a very smooth setting, then it probably deviates. Yeah.
So to some extent, you're using the smoothness of the driving to help you out.
Yeah, definitely. But also non-smooth.
To populate the low modes.
But that's sort of the roughness of it. Yeah, I'm using the fact that it reaches all high frequencies.
Yeah, you have to have that too.
So exactly, it's a combination of smoothness and roughness. It can't be.
You don't want it to be too rough, but.
Yes, it can be so below regular for any number, but it can't be better than that. Well, it could be. I just don't know how to prove it.
There's no other question. Thank you very much again.